Good afternoon. Let's start our lecture. Now, in the previous lecture, we discussed about the superposition of two waves. That is interference. Interference is just another name for superposition of two or more waves. Okay. Now, in the previous lecture, we consider the superposition of two waves with the same frequency, same wavelength, and traveling in the same direction. So the resultant patterns depends on the phase between the two waves. If the two waves are in phase, then the amplitude will be trace the individual values, and if the two waves are pi out of phase, that is half of a wavelength out of phase, then the resultant is strictly zero. So these are the constructive and destructive interference we learned in high school. And for the value of phi, the phase difference in between 0 to and pi, then the amplitudes, of the resultant wave will take on a value between 2 u0 and 0. Trace the initial amplitude and 0 between that. Okay. Now we are going to consider another situation, and that is the problem of standing wave. Now we still consider we still want to consider two waves of the same amplitude, same wavelength, and same frequency, but they are now traveling in opposite direction. So that for the first wave, we have the factor sine kx minus omega t. The relative difference in sign between the omega and k. You notice that the sign before omega is minus and the sign before k is plus. So the sign are different, and that means the wave is traveling in the positive x direction. Now for this wave, the amplitude is the same. The k and omega, the wavelength and the period are the same. But now the wave is traveling in the negative x direction because there's a plus sign there. Okay, the plus sign means when you see omega and k, they're of the same sign. That means the wave is traveling to the negative x direction. So essentially, the two waves collide with each other. So let's see what happens as they collide. Now the formula again tells me that if I have a sine A added to sine B, then I have 2 sine A plus B over 2 cosine A minus B over 2. So this is my A, this is my B, right? So this is A plus B over 2 for the sine, and A minus B over 2 is for the cosine. Now you immediately see that for the first factor, for the sine factor, you don't have the omega t. The omega t cancel, and you simply have a kx for the sine factor. And for the second factor, for the cosine factor, you can see the kx cancel, right? But you now have 2 minus omega t divided by 2. And because the cosine is an even function, the minus sign doesn't matter. And so you have cosine omega t. Okay, so you now have this dependence in space and time. It's equal to the product of the sine factor, which is a spatial dependent, and a cosine factor, which is the temporal dependent. Okay. Now this is obviously not a traveling wave. It is not a traveling wave because a traveling wave should have a factor that either goes as kx minus omega t for the sine or kx plus omega t for the sine function. You should have that trigonometrical factor that involve kx minus omega t or kx plus omega t. But now we don't have that, right? We have the time factor and the spatial factor separate from each other. This factor in red, it depends only on time. It does not depend on position because it goes as cosine omega t. While for this factor, the blue factor, depends only on position but not on time. So the two factors now become separate, and it's obviously that it does not represent a traveling wave along the string. So what kind of pattern does it represent? Now we look at it in this manner. Now the spatial part actually describes the wave pattern. Okay, so essentially that is a sine function. It means the wave pattern is always fixed, right? Because it's always a sine. Okay, it's always a sine. A sine goes like this. Okay, you can see at x equal to 0, for example, the disturbance is always 0 because sine k0 is always 0, right? And also for at a certain point, you may find that the amplitude is always greatest, and at other points, the amplitude is always a 0. So that is obviously a fixed pattern. So the wave pattern is fixed. And the maximum point always remains maximum. The minimum, the 0 point always remains 0. So this is not a propagating wave. Now we can regard this factor 2u0 multiplied by cosine omega t as an amplitude. But since cosine omega t depends on time, it means the amplitude depends sinusoidally on time. It varies sinusoidally on time. So you can imagine that the wave pattern is fixed, but now because of you multiplied a time varying amplitude, so it goes up and down. Okay, it varies between 2u0 and minus 2u0, so it goes up and down. You write it like this. Okay, so the resultant pattern is a so-called standing waves. And on a standing wave, there are points which oscillate with the greatest amplitude, and these are called antinodes. 波幅 in Chinese called 波幅. At this position, the waves always vibrate at greatest amplitudes. And there are positions on the waves in which the disturbance is always 0. It's always a rest. And this position are called nodes. So you have nodes and antinodes alternatively separate along the waves. So that is the so-called standing wave pattern. Now this is a picture which allows you to understand why a standing wave will form when the two waves of the same frequency, same amplitude, same wavelength superpose. Okay, when they are traveling in the opposite direction. Now suppose at a certain instant, at this instant we call t equal to 0, the two waves are in phase. So the disturbance will add up, right? Because the peak is at the same position at the peak, the trunk is at the same position at the trunk of another wave. So they superpose to give a greater disturbance. So you can see a resultant wave has twice the amplitude of the original of the individual original waves. Okay. Now suppose now we wait for a certain time. The time is equal to a quarter of a period. A quarter of a period. So this wave traveling to the left, this wave traveling to the right, and after a quarter of a period, the two waves become pi out of phase, becomes half a wavelength out of phase. And now you can see the peak of the first wave superposed with the trunk of the other, and vice versa. The trunk of the first wave superposed with the peak of the other. And so the two waves are always anti-phase, right? And so the disturbance will be 0. Okay, so now you see a 0 disturbance here. Now still after half of a period, the two waves will be superposing constructively again. The peak corresponds to the peak, the trunk corresponds to the trunk. So it results as another maximum disturbance. Okay. Now, but the maximum at here is different from the maximum at t equal to 0. And for t equal to 0, these two are peaks, right? The middle one is the trunk. But now you can see the middle one is the peak, and these two are the trunk, right? So you can see that the wave, the alternative position of antinodes, they vibrate in antiphase. Okay, when one goes to maximum, the other goes to minimum. When the other goes to maximum, the original one goes to minimum. So it vibrates something like this. Okay. And still after quarter of the period, the two waves add up to 0. And still after half of a quarter of the period, when it's complete the whole period, it returns to its original shape. Okay. So you can see the two waves vibrate like this. So because the wave does not propagate, it simply vibrates up and down at its original position, right? So it is called a standing wave. Okay. Now this is the standing wave pattern. Okay. Now the blue lines indicate the position of the knock. The blue line indicates the position of knock. At the position of the knock, the disturbance is always 0. And the pink line indicates the position of the anti-knocks. And at this position, the disturbance is always the maximum. Okay, but now you can also see adjacent anti-knock. They are anti-phase. One go up, the other go down, and the other go up. The first one go down. So it becomes something like this. Okay. Now the figures below shows you why the standing wave pattern is formed. You consider 2 traveling waves in opposite direction. The red ray is to the left. The blue ray is to the right. It's traveling to the right. When they superpose with each other, you can see there are points at which the 2 waves are always anti-phase, and that becomes the knock. And you can also see there are points in which the 2 waves are always adding up in phase, and that becomes the anti-knock. Okay, so by examining this figure, you can actually see why there are static position of anti-knock and knock. Okay. Now let's see. Let's find the position of the knock and anti-knock. Okay. Now for this factor, because we've said the sine kx factor determines the wave pattern, right? The cosine omega t only gives you the variation with time, right? So the pattern, the standing wave pattern is actually determined by sine kx. So the anti-knocks corresponding to the largest disturbance either in the positive direction or negative direction. So for the anti-knocks, it means the sine kx factor is the maximum, has an absolute largest absolute value. So that means the sine kx is either +1 or -1. Then that corresponding to the anti-knocks. Now, I don't know if you know how to solve this equation. Now, what value of angle that will give you a sine equal to +1? And you may say it's pi/2, it's 90 degrees, right? When I say sine kx equal to -1, then you may say the solution is 270 degrees or 3 pi/2. Is that right? Now, but we have a general solution for that. Instead of having only 2 solutions for the angle that lies between 0 to 2 pi, we also have other solution corresponding to the angle larger than 360 degrees or 2 pi. Okay, so the general solution can be written as this: n plus 1/2 pi, where n is a 0 or integer. Okay, maybe I should write as 0 or integer. Anyway, I think you know the integer including the 0, and it's okay. So when it's 0, it's pi/2. When it's 1, it's 3 pi/2. When n is 2, then that corresponding to the same angle of pi/2 again, but just 1 cycle added to it, and so on and so forth. Okay, so this is the general solution. And you can also have n equal to negative. It can be negative integer and 0. Okay. Now, because I know that k is 2 pi over lambda, right? So 2 pi over lambda multiplied by x is equal to n plus 1/2 pi. So I cancel the pi and I move all the factors to the right-hand side, and I find the position of the anti-knocks as n/2 plus 1/4 multiplied by lambda. So these are the position of the anti-knock. Okay, if you substitute different values of n equal to either a positive integer, negative integer, or 0, you get different position of the knock, anti-knock. Okay. Now you can also find the position of the knock. The position of the knock always has 0 disturbance, so it corresponding to sine kx being equal to 0. Now, what is a solution for this? The solution for this is kx equal to n pi, where n is an integer. Okay, and that means 2 pi over lambda x is equal to n pi. After canceling the pi, you have the position of the node as n over 2 lambda, right? So these are the position of the node. If you substitute different value of n, then it has a different node position of the node given to you. Okay. Now you can see whenever I advance 1, when I increase n by 1 or decrease n by 1, the position actually changed by half of lambda. Okay, because this is n over 2, this factor is n over 2 multiplied by lambda. This factor is also n over 2 multiplied by lambda, right? So when n changed by 1, the position changed by half of lambda, half of a wavelength. Okay, so that means adjacent antinode, if this is antinode, the other antinode separate from each other by half of a wavelength. Also, adjacent nodes, okay, also separate by half of a wavelength. Okay, now you can see very clearly from this figure. Now this is a full wavelength, right? You can see this is a full wavelength. From here to here is a full wave. So the nodes, the adjacent nodes, separate by half of a wavelength. This also separate by half of a wavelength, right? And the anti-nodes position also, the two red line also separate by half of the wavelength. Okay. Now, but I just showed you how to find the position of the anti-nodes and the nodes. This is the general method. You simply set kx, that the sign factor of 2 plus 1 or minus 1, and the sign factor to 0 here. And you actually don't need to memorize this result, okay? Because different problem may have different trigonometrical function. You may have a cosine function here for other problems. So this method is general, but don't memorize the result. You have to do it when you need it. Okay, when you are told in the exam or in your homework to find out the position of the nodes and anti-nodes, you always set this factor to +1, -1, or 0. Okay, and you don't need to memorize this result. Now, in our previous discussion, we always deal with a wave traveling in an infinite long string, right? The wave travel to the right or to the left, but it seems that they are not returning. They will travel to the right or to the left to infinity. Okay. Now we are going to consider a more realistic situation. For practical situation, we always have a string with a fixed length. And for most of the practical situation, we tend to tie the string at both ends. So when we tie the string at both ends, we don't allow them to move at these two positions. Okay, we don't allow the string to move at these two positions. So this, if there's a standing wave forming or not, this position must correspond to a node. Okay, and we are now going to find a wave pattern, that satisfies the wave equation, and at the same time satisfy this so-called boundary condition. Now the fixed end is a kind of boundary condition. It gives the value of the disturbance at a certain fixed point on the string. So it is called the boundary condition. At the boundary, the U value is fixed. Okay. Now we have shown that this is formed. A standing wave can be formed by two waves traveling in opposite direction with the same frequency and wavelength, right? When the two waves traveling in opposite direction, then that would be a standing wave. Now, how do we deal with this problem? We will show you that a standing wave solution can satisfy the wave vibration in this problem and also satisfy the boundary condition. Now, the physics behind is like this. If you have a vibration on the string here, there would be waves either traveling to the left or traveling to the right. But when the wave meets the dead end, this two end is fixed, it is reflected back. Okay, so the two waves just travel back and forth like this. Okay, when it meets the dead end, it reverts itself and travel to the opposite direction. So eventually, when the two waves are traveling back and forth like this, a standing wave pattern will form. Okay, and I will let you see that the standing wave solution that we have just derived is indeed a solution to this problem with a suitable boundary condition. Okay. Now, we already shown that this wave is a solution to the wave equation because can be formed by a superposition of two waves, which are the solution, right? So the sum must also be a solution, right? So we don't need to prove it again. Now we now want to satisfy these two boundary condition. At the left end, we call the left end x equal to 0. Okay, suppose we fix it here. We see that with this sign kx, the left end boundary condition is automatically satisfied. Why? Because when we put x equal to 0 in the sign k0 is 0. So that means the disturbance here is always 0. And that exactly satisfies our requirement that this is a fixed end. Okay. And how about the other end, the right end? We assume the length of the string is L. Okay, so the other end is at x equal to L. And we now require, because the other end is also a fixed end, we now require this factor sine KL when x equal to L is 0. Okay, so this is our requirement now. Okay. And if I want this to be 0, that means KL is always equal to n pi, where n is an arbitrary integer. Is that right? That is the only way to make sine KL always 0, right? So that means K is equal to n pi over L. I can solve for K now. But I want to express everything in the wavelength. So in terms of wavelength, so I have to have a better understanding of it. So I put K equal to 2 pi over lambda. And the pi cancel, I solve for lambda. And I can see that lambda is 2L over n. Okay. So with different value of n, I got different lambda. Okay. Now, what is the meaning of this? The meaning is that there are certain standing wave that can exist along this string, which is fixed as both n. Okay. And the wavelength of this wave depends on the integer and integer n. If I put different integer to it, I got different wavelength. And for all this wavelength, standing wave can form on the string. Okay. Now, for example, let's put n equal to 1. When I put n equal to 1, then lambda is equal to 2L. So what wave pattern does this correspond to? Now, this 2n is always fixed. So this solution actually corresponding to this wave pattern. Now, you can see this is only half of a wavelength, right? A full wave will extend to the other side. This is only a maximum without the minimum. So it's only half of the wavelength, right? So that means the length of the string, the length L, is equal to half of a wavelength, which is just given by this equation, right? Is that right? Now, so what would happen if I put n equal to 2? When n equal to 2, lambda is L. So that is a full wave. Now you can see the length of the string is now equal to a full wavelength, right? And lambda is equal to L. What happens when n is equal to 3? When n is equal to 3, then you can see the length of the string is equal to 3 lambda over 2, or 1.5 wavelength, which is in this case. Okay. In this case, L is equal to 3 over 2 lambda, which is 1.5 wavelength. Okay. Now, so when n increase, you can see when n increased, there are more anti-nodes here. N equal to 1, you got 1 anti-nodes vibrating up and down. For n equal to 2, you now got 2 anti-nodes vibrating up and down. And for n equal to 3, you now got 3 anti-nodes vibrating up and down. Okay, so that is the resulting wave pattern. And of course, for larger value of n, for n equal to 4, n equal to 5, you got 4 antinodes or 5 antinodes, and you will see the wavelength will become shorter and shorter. But the wavelength are discrete. only certain wavelength that is given by this equation, that's given by this equation, can exist on the string. Not all the wavelength can exist on the string. Only certain wavelength unsatisfied this condition can form a standing wave on the string. Okay. Now, so let's examine the frequency also. Because we know that the velocity is given by omega over k, right? This we have derived. So that means omega, the frequency is given by kV. Is that right? Now, but the k is fixed by n, right? Here we have the relationship between n and k. For different n, different integer n, you have different k. So you'll only have the allowable discrete value of k, not continuous. So that means you also will have discrete value for omega. Okay, since k is equal to n power over L, omega is equal to n power b over L. Okay, so for a standing wave to occur on a string which is tied at both ends, which is fixed at both ends, the frequency must take on certain discrete value. Okay, only certain frequency of waves can exist as a standing wave on the string. And this frequency are given by the following. Okay, either pi v over L for n equal to 1, 2 pi v over L for n equal to 2, and n equal to 3, and so on. Okay, so this frequency I can have a standing wave form on the string, but not other frequency. Okay, so in order for a standing wave to form, you have to excite the string at this particular frequency. Other frequency will not work. If you excited the string with other frequency, then there will be a rather chaotic wave pattern vibrating on the string, but you cannot see the standing wave pattern. Okay, if you want to set up the standing wave pattern, you always have to apply this frequency to vibrate the string. Okay, so this is the principle. So we can write down the standing wave solution for a string fixed at both ends in terms of the integer n. Okay, we know that omega is n pi b over L, so we replace omega with n pi b over L. We know that k is n pi over L, so this replaces n pi over L. So this becomes the solution. This is a solution, standing wave solution for a fixed string, for a string fixed at both ends. Okay. Now, I just want you to have a taste of it, since you are not very familiar with this kind of algebraic manipulation. So let's have a simple example. Suppose now we have two waves. They are obviously of the same wavelength and frequency, and also the same amplitude. But you can see one has a plus sign, one has a minus sign in K. Okay, the others, the sign of omega are the same. So they represent wave traveling in the opposite direction. Okay, and you can see when they have the same frequency and wavelength at the same amplitude, they form a standing wave. Okay, so I want to challenge you. Please work for 3 minutes to find the superposition. Okay, to find the standing wave position, and also find the position of the nodes only. Now I give you the hints. I hope you remember that formula. It's a superposition of the sine function. If you have sine A added to sine B, that become 2 sine A plus B over 2 cosine A minus B over 2. Okay, so try to work on apply this on these two waves and see what standing wave you got. Okay. So what is your answer? Have anybody got the answer? Now, it's not difficult. The resultant U is U1 plus U2, right? And because of this formula, we have 2 multiplied by 0.06, which is the amplitude. The first factor is a sine, right? The first factor is sine. Now, this factor is A, and this factor is B. If I have A plus B, then the pi x has gone, right? Because they cancel. And x pi t, the 2x pi t divided by 2 will give me simply x pi t. Is that right? And how about the minus the cosine factor? For the cosine factor, we have this A minus B. So the 8 pi t has gone. The minus pi t minus 2 pi t divided by 2. So it's minus pi t. But the cosine factor does not matter for the minus sign. So I have a pi t here, pi x here. Okay. So this is a standing wave pattern. Oh, sorry, I read it wrong. And the position of the nook correspond to what? Corresponding to this factor being equal to 0. Right? Because it's always 0 disturbance here, right? So it's corresponding to this factor being equal to 0. So what is the solution for that? It corresponds to pi x. Now, the 0 of the cosine is either pi over 2 or 3 pi over 2, right? Is that right? So that means it is n, the integer, plus 1/2 pi, where n is the integer. These are the value when the cosine is 0, right? Either 90 degree or 370 degree, or for more cycle, right? More cycle around, you have larger n. So the pi will cancel on both sides, giving you x is equal to n plus 1/2. So this is your answer. Okay. Now this question asks you about the amplitude, period, and wavelength. I think you know how to do it, right? The amplitude is 0.6. The wavelength, you can find it by setting k, which is 2 pi over lambda. 2 pi over lambda equal to pi, right? So the lambda is equal to 2 meter. Is that right? And the omega is equal to what? Omega is equal to 2 pi over t, and 2 pi over t is equal to 8 pi, right? So you now have the period equal to 1/4 of a second, right? So that is easy to find. Okay. Now, so we review our result. Our result is that if you have a string of length L fixed on both ends, there are certain standing waves that can exist on the string, and in fact there are infinite many of them. If you go to a larger n, then the wavelength becomes shorter. Okay, you have more antinooks here in the wave, and you can have n goes to infinity theoretically. Now, so that constitutes different solution to the wave equation with this boundary condition. Okay, and this solution, all this standing wave solution, that's can exist on the string satisfying the fixed end boundary condition, they are called normal mode. Okay, normal mode refer to this solution. Okay, now we don't write the amplitude here, but you know that this cosine factor multiplied by the sine factor, this is a t factor, this is the x factor. When these two multiplying together, I call this a normal mode solution, which is denoted by n. Different n here corresponding to the n value here. So you have different standing wave solution for different n. Okay, so you have n equal to 1, 2, 3, 4 up to infinity. So this form many solution, infinitely many solution, and they are called the normal mode. Now, but what determines the frequency and the wavelength? We know that the frequency, the angular frequency is n pi v over L, and the wavelength is, and the wave number is n pi over L, right? This determines the wavelength and the frequency, right? Now, but you can see, both the wavelength and the frequency, they depends on what? They depends on the velocity of in the medium, the velocity of travel on the waves. Okay, because now you have the frequency as n pi v over L, right? So that depend on v. Okay, so the frequency does depend on the wave speed, and the wave speed actually depends on the physical property of the medium. It depends on the tension divided by the density square root, and that is the specific to each string, because this is a physical property of that string. Okay, how tall you stretch it. Okay, and that is the tension. And what is the density? What kind of material you make to use it to make it? That is density. It depends on the tension and the density. Okay, so that is the velocity. So with what frequency you want to excite the wave depends on the frequency. And it also depends on the length. Okay, that is the boundary condition. At the n x equal to 0 and x equal to L, the two ends are fixed. Okay, and these are called the boundary condition. Okay. Now, why we are so much interested in this normal mode solution? Okay, why are we so interested in it? The answer is given by Fourier. Fourier is a famous mathematician in the 19th century, in the late 18th to early 19th century, and he has just proven that any vibration, arbitrary vibration on the string, on the taut string, can be written as a superposition of the normal mode solution. Okay, so we choose a set of coefficients. Now these are the amplitude for individual normal mode. Now for different n, now we form a summation over this normal mode solution. This summation runs from n equal to 1 to infinity. Okay, so each term corresponds to a certain normal mode solution of a specific n. And for this normal mode solution, we are here it with a certain amplitude, which we call Cn. Okay, and if we choose a Cn carefully by the so-called problem for Fourier analysis, then we can make this infinite series to fit any vibration, any modes of vibration of the string. Okay, now for example, here we have a square wave. The blue curve is a square, right? It does not look like a sine or cosine. It's a square. And you cannot match a single sinusoidal wave to a square wave because they are of different shape. Okay, so if you match one solution of a sine wave, this is a standing wave solution, to a square wave, they do not look like each other. Okay, there's a lot of difference between them. Okay, although the period is the same, but they're obviously different. But how about if you add one more mode? If you add high frequency mode with another constant C2, okay, or C3, you depends on the superposition, then you have a better approximation to the square wave. Okay, because you can use a small modulation here to make the top or the bottom more closely like a flat top. Okay, and you can do better by adding more higher frequency shorter wavelength modes. Okay, and you can see as we are here, we only have at 4 terms, and you can see the addition of 4 terms of this is already getting very close to the square wave. If you add infinite many of terms with suitably chosen Cn, then you can straightly produce this square wave by using an infinite series of the normal mode solution. And this is called the Fourier analysis. Now, the Fourier analysis expresses a general wave pattern, whatever vibration, not necessarily periodic, in terms of the sum of normal mode solution. And that is a very general method in physics and engineering. In physics and engineering, we always pick up a signal from something. For example, we pick up a signal from a distant star with different frequency light. Or for example, we use a recording machine to record the sound of a musical instrument, and they have different frequency. The sounds have different frequency. So we do a Fourier analysis to know its component frequency, to know what kind of frequency do the sound or do the light carry. Okay, so this is called the Fourier analysis. We decompose it, okay, into the so-called Fourier component. Okay, and on the other hand, if you are given an arbitrary shaped vibration, you can also construct that's vibrating that shape of waves by superposing different Fourier component, different normal mode solution by choosing a suitable Cn, suitable set of Cn. Okay, so this is the 2 sides of the Fourier analysis. Okay. Now, let's have a break now. We just have finished all our discussion on transverse waves. So we have a break for 10 minutes. And after that, we will proceed to different kinds of wave, which is the longitudinal sound wave. Okay. We will see how the compression and rarefaction of air propagating just like a sinusoidal wave we have encountered before on the string.